Thank you very much for the invitation, for the opportunity to give a talk at this Flash Talk series. What I'm talking about is a joint work with Eric Hanson, Sunny Rohr, and Ralf Schiffler. And our starting point was really a paper by, I refer to it as the three Emilys and Ralf, where they studied certain combinatorics of quiver representations of type A. And in particular, they study MAR modules, maximal almost rigid modules. So let me get into this. We have a type A and quiver. Type A and quiver are very well known. The Auslandereiten quiver would have a shape, something of this form. And one particular property of that Auslandereiten quiver is that whenever you take two indecomposables, 2 points in the Auslandereiten quiver, then the possible non-split short exact sequences between those two modules x and y are of one of two forms. Either you have two indecomposable middle terms, so if you put your x here and your y there, so to say, then the middle terms would be, the middle terms would be sitting here. So you have two middle terms. And the other sort of short exact sequences is the one where you have only one indecomposable middle term. So if you would have placed your x and your y here, then there would be one indecomposable middle term, and you see that sort of in that rectangle, one of the corners would be zero. So that's the phenomenon. There's only exactly these two sorts of short exact sequences non-split between indecomposable middle terms. So what they were doing now is the following. Uh, First, let's start with a basic module, no repeated indecomposable summons, and then a module is called rigid if it has got no self-extensions. And the three Emilys and Ralf were kind of generalizing that notion by saying a module M is almost rigid if it does not have between two direct summons x and y, if it does not have uh, non-split short exact sequences of the first kind. Yeah. So they kind of weaken the condition of being rigid to they do not allow the short exact sequences of type 1 to appear, but they do allow these kind of degenerate non-split short exact sequences. So, okay, so this is their definition. Um, and then they call module maximal almost rigid if it's maximal with respect to that property. So if it is almost rigid, but whenever you add some different summons, then it's no longer almost rigid. And nice result is in their paper, they have established a bijection between those MAR modules, the maximal almost rigid ones, and triangulation of polygon with n+1 vertices. And those triangulations of an n+1 gon are very, very well studied. This is a beautiful combinatorial object. We do know there's a notion of flip between triangulations, and the flip corresponds to a mutation of those MAR modules. So that kind of is similar to the cluster algebra story, but notice we are here completely inside the module category. And what we change is that we kind of change which short exact sequences we do allow to consider. So here comes the flash talk moment. I mean, this is a flash talk, so where's our flash, our inspiration? We start like, can we replace this almost rigid notion by rigidity with respect to something that is called an exact structure, because an exact structure, after all, is a subset of all of the set of all short exact sequences, and this is kind of what they do. So, is there a good, nice exact structure that exactly models their notion of almost rigidity? That's the question. And so let me go a little bit into this. what is an exact structure? Let me start with that. An exact structure can be seen as an additive sub-bifunctor E of the bifunctor x1. So we have x1. We know that we can realize x1 as equivalence classes of short exact sequences, and due to Reinhold-Baer, this enjoys being a vector space. There's a sum and everything. So when we have an additive sub-bifunctor E of this functor, which is closed, then this is called an exact structure. Okay, a little mark, the functoriality we multiply by maps here by performing push out or pullbacks. So your subset need to be closed under pullbacks and push outs. And a second thing, this property of being closed is whenever we have two short exact sequences in the exact structure with monomorphisms I and J such that you can compose them, then there is also a short exact sequence in E which starts with the composition of these two monomorphisms. So this is closed under composition of monos. And dually, it's also closed under composition of epis, as Carlo Klaproth already pointed out earlier today. Okay, good. So exact structures are nice because they provide a framework you can do where you can do kind of a homological algebra relative to your chosen set of short exact sequences. You can define relative projectives, and then you do resolutions with respect to those. You can define a derived category. And you can generalize all sort of things that have been defined. You can generalize the notion of rigidity by saying a module is E-rigid if that subfunctor of evaluated on MM is 0. Good. So this is the general framework. And let me jump right into results. So we found there is an exact structure which we call E diamond. That means there's kind of two middle terms. There is an exact structure such that a module is rigid with respect to that exact structure if and only if it is almost rigid. So we can realize the notion really in using the machinery of exact structures. Moreover, you can define also not only rigid, you can define tilting, and the module is tilting relative to E diamond if and only if it's maximal always rigid. And moreover, the category of modules endowed with that exact structure is an zero Ausländerheiten category in the sense of Gorski, Nakaoka, and Palü. So this means it has relative global dimension at most 1 and relative dominant dimension at most 1. And Gorski, Nakaoka, Palü showed that for zero Ausländer categories, there's a nice theory of mutations. All the maximal rigid ones all have the same number of objects and you can mutate them. And this mutation coincides with the mutation that the three Emilys and Ralf have introduced. So everything fits nice into that context. And let me just say a word on how do we construct, how do we find that exact structure. In generally, it's difficult to describe an exact structure by it is this explicit set of short exact sequences. Yeah, there's a better way to define exact structures by Auslander and Solberg. It is sufficient if you specify which Ausländerreiten sequences you want to belong to your exact structure. And we choose on this A type AN Ausländerreiten quiver, we choose the sequences which have two middle terms, the Ausländerreiten sequences which have two middle terms. We want them to be in our exact structure E diamond, but the others with one middle term, we do not want them. And you can then verify that for any two given indecomposables, really this E diamond XY is made up of sequences that, if they are not split, have exactly two middle terms. This is exactly the characterization that was used in the paper by the three Emilys and Ralf. And just as a little remark that it's not always that easy, it's not always that trivial. If you go into type D quivers like this quiver here, and you look at a short exact sequence here given by these two end terms. So my end terms would be this and that module. This is the wrong color coding. My end terms would be x and y. Then there's a short exact sequence which has these two middle terms. Great. So we have a short exact sequence that has got two middle terms. Now you take the push out along this morphism, and then you find a short exact sequence which goes like so, which has one middle term. So what does that tell us? In type D quivers, the set of short exact sequences with two middle terms is not closed under forming pushouts. So it does not form an exact structure. So in general, this is a non-trivial statement, yeah. And luckily in type A, it does work. That's basically my message. Uh, Good, thank you very much.